Welcome back to the deep dive. Today we're diving into something pretty fundamental for engineering safety, how we simulate things breaking. Specifically, structural failure. We're looking at phase field models. These are really powerful tools for predicting how cracks start and grow in materials. Think airplane wings, bridges. You need to know how they might fail.
Absolutely essential stuff.
But here's the catch. These models, while powerful, lead to some seriously complex math. The equations are highly nonlinear, non-convex, basically a nightmare to solve reliably. And our source material points out that standard solvers often just, well, fail. They diverge, especially when the failure happens quickly, what the researchers call brutal crack evolution. Kind of paints a picture, doesn't it?
It does, and that's been the big headache. If you absolutely needed your simulation to run without crashing, especially during those unstable moments, you traditionally relied on something called the alternating minimization algorithm, or AM, sometimes called a staggered algorithm.
Okay, AM. Why was that the go-to?
Well, it's robust because it cleverly sidesteps the trickiest part. It decouples that complex non-convex problem into two simpler sequential steps. It solves for one variable, then the other, back and forth. It basically guarantees convergence. It just works.
Ah, so it's reliable? But I sense a but coming.
There's always a but, isn't there? The but here is speed, or rather the lack of it. AM is notoriously slow.
Right.
To accurately track how the material behaves, especially near the point of failure, it needs a huge number of iterations. You often have to take incredibly small steps in your simulation.
Which means computationally very expensive.
Exactly. Makes large, complex simulations almost impractical, or at least prohibitively time-consuming.
Okay, so that sets the stage. And the mission for this deep dive is exploring some research that claims to have found a major shortcut, a way around this slow, steady AM approach.
That's right. They've combined a modified version of a different solver, L-BFGS. We'll unpack that with a specific novel line search technique.
L-BFGS. That's Limited-memory Broyden, Fletcher, Goldfarb, Shanno. Quite a mouthful.
It is, yeah. We usually just say L-BFGS.
Got it. And the claim is pretty bold. This L-BFGS combo makes these fracture simulations 5 times faster on average. And crucially, without losing the accuracy engineers need.
That's the headline, yes. 5 times faster, same accuracy. It's a significant claim.
Okay, let's dig in. To really appreciate why this is such a potential game changer, maybe give us a quick refresher on the phase field idea itself. Why use it in the first place?
Sure. So phase field modeling is actually quite an elegant solution to a tricky problem.
Yeah.
Tracking a physical crack, a sharp discontinuity that suddenly appears and grows, is computationally very difficult, especially in complex 3D shapes.
You'd have to constantly remesh or track the crack tip explicitly.
Precisely. Very messy. So phase field takes a different approach. Instead of a sharp crack, it approximates it as a narrow, diffuse region. Think of it like smearing the crack out over a very small width.
Okay, like a fuzzy crack instead of a sharp line.
Exactly. And it uses a special variable, usually called phi-flee, a scalar field, that smoothly transitions from 0 in the intact material to one where it's fully broken.
Ah, so it's like a damage indicator spread across that fuzzy region.
You got it. And the beauty is, the evolution of this phi field, the crack growth, becomes part of the system's governing equations naturally. You don't need complex geometry tracking. It just emerges from the solution.
That does sound elegant, but you mentioned earlier this leads to non-convex energy functionals. That's the downside.
That's the core difficulty, yes. Non-convex means the energy landscape isn't a simple bowl shape where you just roll downhill to the lowest point, the solution. It has lots of local minima, bumps and valleys.
Like trying to find the lowest point in a mountain range instead of a smooth valley.
Good analogy. And standard solvers, monolithic ones like Newton-Raphson, they can easily get stuck in a local valley, or worse, when the crack starts growing rapidly and the landscape changes violently, they just lose their footing completely. They diverge.
That's the brutal crack evolution problem again.
And that's why AM was invented for this. It avoids getting lost in that complex landscape by breaking it down. Fix the crack state, solve the easier convex problem for the material's displacement, then fix the displacement and solve the easier convex problem for the crack state. Back and forth.
Sequentially solving simpler problems makes sense why it's robust.
Very robust. But each of those steps and the many iterations needed between them to converge at each load increment, that's where the time goes.
Okay, so AM is safe but slow. Now let's bring in the speed demon, L-BFGS. You said it's a quasi-Newton method. How does that help with speed?
Right. Quasi-Newton methods are all about efficiency. Standard Newton methods, the gold standard for many problems, have a big cost. They need to calculate and then invert or factorize what's called the tangent stiffness matrix, or the Hessian, at every single iteration.
And that matrix is big for large engineering problems.
Huge. If your problem has dim degrees of freedom, think millions for a complex structure building, and factorizing that matrix takes effort proportional to dim squared, that cost dominates the computation.
On Keck sounds expensive. How does quasi-Newton, like L-BFGS, get around that?
It approximates that expensive Hessian matrix. Instead of calculating it directly, it builds up an approximation using information from previous steps, specifically changes in the solution vector and the gradient vector.
Ah, so it uses history to guess the curvature.
Exactly. And the clever part is it does this update very efficiently. The computational effort per iteration for L-BFGS is only proportional to the dimension itself.
Wow, okay. From dim squared down to just dim. That's a massive difference, especially for large dim.
It's the key difference. Think millions squared versus just millions. It fundamentally changes the scaling of the problem. That's where the potential for huge speedups comes from.
And the L in L-BFGS stands for limited memory. Why is that important?
Right, because even storing the approximated full Hessian matrix could be too much for very large problems. L-BFGS gets even smarter. It doesn't store the approximate matrix itself.
Oh, what does it store then?
It only stores a small number, say m, of the most recent update vectors, the changes in the solution and the gradient. Typically, m is tiny, like 2 to 8.
Just a handful of vectors, regardless of how big the overall problem is.
Exactly. So the memory requirement scales linearly with the problem size, not quadratically. This makes it feasible for massive simulations where storing a dense matrix, even an approximate one, would be impossible.
Very clever. Memory efficient and computationally faster per step.
But wait, didn't the researchers use a modified L-BFGS? Why modify it?
Good catch. Yes, they did. The standard L-BFGS update formulas are generally derived assuming the problem is convex, or at least well-behaved. But we know phase field problems are decidedly non-convex, especially during crack growth.
So the standard assumptions break down. They can, yeah. The researchers found that a specific modified update formula, one designed with non-convex functions in mind, performed better and was more robust, particularly during those brutal steps. Their tests, like on the bar under tension example around step 50, showed the standard L-BFGS could struggle while the modified one kept going efficiently.
Okay, so modified L-BFGS gives faster steps and uses less memory. But we still have that fundamental problem, non-convexity. Standard L-BFGS, even modified, isn't guaranteed to converge on these tricky problems, right? Especially when the crack goes unstable.
Precisely. That's the absolute crux of the matter. Speed is pointless if the solver crashes halfway through. And this brings us to the real innovation in this research, beyond just using L-BFGS. It's how they kept it stable.
The line search strategy you mentioned earlier.
Exactly, the line search. But there's a complication specific to phase field models that makes standard line searches problematic.
Oh, what's that?
It's related to how these models ensure cracks don't heal themselves, which would be physically unrealistic. They use an internal history variable, often called mathcal-may.
A history variable. What does that track?
It essentially remembers the maximum amount of damage energy or strain energy density that each point in the material has ever experienced. The crack can only grow or stay the same based on this maximum past value. It can't reverse if the load decreases.
So it enforces irreversibility. Makes sense.
No.
What's the complication?
The complication is that this history variable means the system is no longer strictly following a path that minimizes a single global energy function at all times. It breaks what we call variational consistency.
Uh-oh. Why is that bad for the line search?
Because traditional line search methods rely fundamentally on monitoring that global energy functional. They work by ensuring that each step taken actually decreases the total energy, guiding the solver downhill towards the minimum.
But if the energy isn't consistently decreasing because of the history variable?
Then monitoring the energy value becomes unreliable. A step might look like it's increasing the pseudo-energy, even if it's the physically correct step towards equilibrium. The theoretical basis for those energy-based line searches just falls apart. They might fail to control the step size properly, leading to divergence.
Okay, wow. So the very thing that makes the physics right, no healing, breaks the standard stabilization method for the solver. How did they get around that?
This is where their novel line search comes in. Instead of monitoring the energy value, they decided to monitor the energy gradient, specifically the derivative of the energy functional with respect to the step size, lambda.
Okay, explain that. They're looking at the slope instead of the height.
That's a perfect way to put it. They monitor the absolute value of this derivative, tilde lambda. The line search procedure then iteratively adjusts the step size lambda in each L-BFGS iteration to find the point where this absolute slope is minimized.
So find the flattest point along the search direction, regardless of the actual height energy value.
Exactly. It's a condition that ensures mathematical robustness and finds a suitable step size, even when the underlying energy functional isn't behaving nicely due to that history variable. It doesn't rely on variational consistency.
That is really clever, a mathematical workaround. And does this gradient-based approach have other benefits?
It does. It has a dual function, really. First, it acts as a brake. When the simulation hits an unstable patch, like rapid crack growth, the line search will naturally find a step size lambda lamb less than 1. It shortens the step, preventing the solver from overshooting and diverging. This provides the needed stability.
The safety net.
The safety net, yes. But second, it can also act as an accelerator. In smooth, stable parts of the simulation, the line search might find that the optimal step size is actually larger than 1 to lambda long.
So it can take bigger steps than standard methods would allow.
Potentially, yes. It can accelerate convergence by taking these more aggressive steps when it's safe to do so. So it's both a brake during tough times and a gas pedal during easy ones.
Brake and accelerator. I like that. Okay, this sounds great. In theory, modified L-BFGS for speed, gradient line search for stability, and even more speed. But does it actually work? Let's talk results. What did they test?
They put it through its paces. They use 4 standard benchmark problems in fracture mechanics: a simple bar under tension, BUT, a single-edge notch plate under tension, SENPT, the same plate under shear, SEMPS, and a symmetric 3-point bending test, S3PBT.
Covering different kinds of loading and cracking behaviors.
Exactly. And they tested it with 2 common phase field formulations, the Tex-Harry-2 model and a cohesive zone model, CZM-inspired one, and compared it directly against the traditional robust AM algorithm.
And the big headline, the 5 times speed up. Did it hold up?
It absolutely did. Across all examples, all models, the L-BFGS algorithm combined with the new line search consistently delivered an average computational time saving of around 5 times compared to the AM method.
5 times faster on average. That's significant. Any particular standouts?
Yeah, a couple are quite memorable. For instance, in the shear test, the SENPS problem, using the CZM model, L-BFGS wasn't just 5 times faster. It was approximately 10 times faster than AM.
Wow, 10 times. That takes a simulation from, say, 10 hours down to 1 hour. Huge difference.
It really is. And another interesting case was the bending test, S3PBT, with the TXT2 model. In that specific test, L-BFGS actually required more total iterations to solve the problem than AM did.
Wait, more iterations but still faster? How does that work?
It comes back to the cost per iteration we talked about earlier. L-BFGS took about 11,400 iterations compared to AM's roughly 9,000. But because each L-BFGS iteration is so much cheaper, math will be effectively hidden inside AM's nested loops. The total runtime for L-BFGS was still 5 times less than AM's.
Ah, okay. That really drives home the efficiency gain per step. Even taking more steps, it wins the race easily because each step is so much quicker.
Precisely. It highlights that iteration count alone isn't the full story. It's the computational cost per iteration that dominates here.
And what about the line search? Was it actually needed? Did LBFGS fail without it?
Oh, absolutely critical. The experiments confirmed it. In the problems known for unstable crack propagation, like the SNPT, tension notch, and S3PBT bending, the LBFGS algorithm without the gradient-based line search simply diverged. It crashed as soon as the crack growth became unstable.
So the line search was the essential safety net that made LBFGS usable for these problems.
Non-negotiable. It provided the robustness that LBFGS inherently lacks in these non-convex history-dependent situations.
And did the combination of the modified LBFGS formula plus the new line search offer extra benefits over just using a standard LBFGS with the new line search?
Yes, they quantified that too.
Yeah.
Using the modified LBFGS update did provide additional time savings compared to the standard formula, even when both used the new line search. For example, with the text-to-2 model in the SMPT test, the full package modified LBFGS plus gradient line search shaved off an extra 10% of the runtime compared to using standard LBFGS with the gradient line search.
So every piece of their proposed framework contributed to the final performance gain.
It seems so. The modified update helps efficiency, especially in tricky spots, and the line search provides the essential stability plus potential acceleration. Together, they make a very potent combination.
Okay, wrapping this up then, what's the big picture takeaway here?
The big picture is that this research offers a really versatile and um, highly efficient computational framework for simulating fracture with phase field models.
Hmm.
Crucially, because that gradient line search doesn't rely on variational consistency, it works for both standard variational models and these more complex non-variational ones that use history variables. That broad applicability is pretty powerful.
And for you, the listener, what does a five-fold speedup really mean? Think about an engineer designing, say, a new composite material for a car chassis or a critical component in a wind turbine.
Hmm.
Running a complex fracture simulation might take 40 hours on a powerful cluster using the old AM method. That's a full work week, basically.
Yeah, easily.
Cutting that down by 5 times means it takes maybe 8 hours, a single workday. Suddenly, running many variations, optimizing the design for safety, doing more rigorous checks, it becomes feasible within a practical design cycle. It's not just faster, it potentially enables better, safer engineering by allowing for more thorough virtual testing.
That's absolutely the impact. It lowers the barrier to entry for performing these crucial safety analyses on larger, more complex systems.
So that brings us to our final provocative thought. The study briefly mentions this L-BFGS approach stays efficient even for dynamic fracture, things breaking suddenly under impact, and for multiphysics problems, where fracture is coupled with, say, fluid flow or thermal effects.
Right, the potential applications are broad.
Right. So given these huge performance gains, making simulations that took weeks, perhaps, finish in days, what engineering safety challenges, previously considered just too computationally expensive to tackle routinely, might now be within reach? Think about things like predicting long-term fatigue failure in aircraft components under millions of cycles, or maybe simulating fracture networks developing in underground rock formations for carbon storage safety, or even assessing damage in biomedical implants over time. Are these previously intractable problems now open for serious investigation using methods like this?
That's the exciting question, isn't it? What doors does this kind of computational speedup unlock for designing safer structures and systems across all fields of engineering? It certainly pushes the boundaries of what's possible.